So hello everyone. For this session, we will be talking about what sequencers are, what are their roles in rollups and L2s, why are they needed, and some variations of sequencers being used in the current state of the art, and what are the proposed sequencer designs for better designs, I would say, for the Ethereum and other layer 1 infrastructures. So starting with what sequencers are. So yeah, so what the fuck are sequencers? Uh, we can say that sequencers are some special nodes that are given some special permissions by rollups or L2s. And what are these special permissions? They can like batch some transactions. They can see the mempool where the transactions are being held, and they can execute these transactions. They can change the state of the L2s, and they are given the permission to also batch and like post it on a roll-up contract or a L2 contract, which would be on L1. And the transaction ordering and inclusion of transactions is also being handled by the sequencers. And yeah, these are some permissions which the sequencers have compared to other nodes, and this is what makes them special. So this is kind of like how a sequencer works. So starting with what these this is a transaction mempool where the transactions are which are being sent to a rollup or a L2. And what happens is sequencers then cherry pick some of the transactions from this transaction mempool which it finds favorable, because of its ability to like select transactions and order the transactions and batch them. It can collect MEV, which is a major source of income for the sequencer handlers or sequencer operators. So after cherry picking the transactions, what it does is uh, it batches and compresses the transactions, and then sends it to a layer 1 chain, where in the layer 1 chain there is a special rule of contract or a layer 2 contract where the transactions are being sent as a call data, not transactions. The entire batch is being sent as a call data. And uh, but the use of there is a special benefit of using sequencers. It can give us a soft commitment before even the transaction is being accepted on layer 1. That is because it has the permission to include transactions and execute it on the layer 2, not on L1. It can confirm that this transaction will be included in the batch that it will create, but it may not be sure of it if it will be executed on the layer 1 or it will be included in the layer 1 too. So it can't give a hard commitment or like a proper commitment that it will be included, but like it can give a soft commitment because of its special permission that it can like include the transaction in its batch. And whenever the uh, batch is submitted on the layer 1 contract and it is settled on the layer 1 chain, the confirmation that the transaction has been settled is given to the validators. What the validators do is now assert the state change which the sequencer made. So what sequencer does is when the batch has been confirmed on the layer 1 change on the layer 1 chain, it also does a change on the layer 2 blockchain. So there is a state change that happens. The list of transaction is the accepted transactions that it included in its batch. And after the state change, the validators assert the state root on the layer 2 blockchain, and then now the sequencers now can create like another batch and then send it to, and the process repeats again. So it has a security because even the L1 validators that are not directly part of it, but since the batch is being sent to the layer 1 blockchain, the L1 validators like can validate that transaction. So security of layer 1 is maintained, and also the layer 2 validators also has a state root on this layer 2. So the securities on L2 is also maintained. And for the current scenario of sequencers being used, most of them are centralized siloed sequencers, meaning every rollup runs its own special node for its purpose, which only serves this chain or its chain. So this is currently a big red flag because like centralized anything that is centralized is in retrospect bad or not favorable because it has a lot of disadvantages. So what issues does it bring? So there is a single point of failure because of the centralization. There was a case when Arbitrum's sequencer was down for 70 minutes, and there was nothing that could happen in that scenario. So they brought a change to the design of how the transactions can be included, which I will discuss later. So, and also there is a risk of MEV exploitation since the sequencer has the right to like order the transaction in any way that it feels. Uh, the sequencer can front run or sandwich the transactions that are in the mempool currently and can favorably include transactions that it can benefit from. So that is a major like point of exploit that the sequencer can bring. So there is also weak censorship resistance. Sequencer can like block the transaction. So it cannot like indefinitely block the transactions. Sometime in the future, it will have to include the transaction. It can't like block it permanently, but yeah, it can like delay the transaction for a really long time, which is issue in itself. And so weak liveness guarantee like uh, so we know that for the UX of a L2s, the benefit that it brings is instant finality, right? So whenever I send a transaction on L2, almost instantly it gets confirmed. So this liveness guarantee is not here. There is no atomic composability and no security or pooled security because one like it is the first step that the transaction has to go through, and now I can't like extract the L1 and L2 security, which was the point of like creating L2 with high throughput, high like instant finality, but also like having the security of the layer 1 chain. Uh, what benefits does the centralized sequences bring is now centralized sequences like have lot of compute power. So the like the lot of compute power in itself brings high throughput uh, advantage. So a lot of transaction can go through, uh, and we don't have to like in a decentralized scenario. We like there can be an issue where low throughput or low computational sequencer gets the right to like sequence the transactions, but so that can slow down the chain, so slow down the transaction penalties of all the transactions that go through. But like that is a separate issue, and we'll like talk about it later. So they Arbitrum had a way of solving it after the sequencer went down for like 70 minutes in like 2022. So what they brought is like Arbitrum now provides a way to force a transaction on layer one. So now I like if the sequencer is malicious or like not responding, what I can do is I'll force a transaction with the force inclusion method, which Arbitrums provides. So with this, I can directly put my transaction on the layer one chain without it having to go through the sequencer. So it is uh, not it not forces the sequencer. It like bypasses the sequencer to accept the transaction on layer one. And the issue with this is that the layer one, I'll have to now pay the fees of layer one, and like also now there is no instant finality, and I'll have to wait for 15 seconds, which is the block time for a Ethereum transaction. So that is a like disadvantage with this. So what is the solution for this? So we have decentralized share sequencers in product in not in production, I guess in production also. So Espresso has it, Astria has it, Radius and Madras Darknet has some decentralized shared sequencers which they have currently. So yeah, first of all, when I'm talking about decentralized sequencer and shared sequencer, they are not the exact same thing. The sequencer architecture can be broken down into two stages. So first of all is if it is centralized or decentralized. So and the other one is if it is siloed or shared. So what the centralized architecture is like, what we discussed earlier. So every rollup runs its own sequencer and for its own chain. That is a centralized sequencer. But a decentralized sequencer would be like now there is no single sequencer that will be running. There can be multiple sequencers, and I'll discuss the architecture of decentralized sequencers later. But in general way, we can consider it like it's kind of like proof of stake, where there is a group and one of them will be like selected for sequencing the uh, for uh, for an epoch of time. So this is how a decentralized sequencer like operates. The other breakdown or the other stages, if it is siloed or if the sequencer is shared. So siloed means that the sequencer that is running is only for a specific rollup or specific L2, or like for a pair or like for a specific rollups only. Whereas the shared sequencer is like there are many rollups that have their own sequencers, but they're running in a shared kind of way. That is what a shared sequencer is. They are sharing the sequences. So it is not like uh, every chain will have its own sequencer running. One of the sequencers from any of the chain can be selected, and it will sequence for all the rollups or L2s that will be like giving transactions to its own mempool. Uh, so the sequencer will be like that sequencer will be getting transactions from all the mempools of all the rollups or L2s, and then will be batching it and giving it to the like L1 chain. So how are we decentralizing a sequencer? So what I discussed, it's very simple. POS-like system where the a group of sequencers will have like will they will stake or they'll have bonds. They can stake their ETH, or they can stake their bonds which they will be having, and for any malicious activity the stake and bond will be slashed, and any reward that they would be getting can be snatched away from them. So and there is a constant rotation of sequencing rights. So now no single point sequencer will be having the right to sequence the data and sequence the transactions that they will be in the mempool, and this maintains the decentralization aspect of like these sequences. And then what is a shared sequencer? That is also like a sequencer can be used for multiple rollups and not specific ones or a particular group set of rollups that I discussed earlier. So this is a nice diagram I found on Twitter. Like this can give an you can get an overview from this rollups with an independent centralized sequencer. So a user is like a user or any specific rollup is like sharing the transaction or like giving the transaction on the rollup, and then the rollup those sequencers then the sequencers then post the batches on the data availability layer, which is like what a normal way would be. And data availability layer can be like Aware or Celestia. And now in a decentralized shared sequencer, for the as like this is the Astria design of the shared sequencer, users post the transaction on the rollups own mempool, but like the shared sequencer will be the one that will be selecting the transactions from all the transaction mempools, and then it will post on every rollup. It can give a soft confirmation that this transaction that I have included in this batch will be included, and it will be given to the data availability layer. I'm not sure if this will be executed on layer one, but I have included this. So this is a soft confirmation. And then the shared sequencer posts it on data availability layer. And then from that, on data availability layer, on each rollup contract, the batch will be given. And then the rollups can like extract the data uh, for the state update that they want to make on their rollup design or L2. So there are some downsides of shared sequencers. And first of all, like even with the decentralization and shared sequencers, there the shared sequencers were like introduced because they since even with the decentralized sequences, there was a problem of that the there was no interoperability in the like the chains. So if I want to like, for example, let's say if I want to like I'm a arbitrage trader and I want to like utilize the liquidity on like say chain B, but I have all my funds on chain A. So what I would have to do currently is bridge the assets from chain A to Ethereum, and then from Ethereum to chain B, and then I can do anything with the liquidity in chain B. So that is a big hassle that and a big design flaw that is currently in uh, the rollup designs, and uh, the the use of shared sequencers like brings the interoperability thing in it, but there is also disadvantages that it brings. So what are the downsides of shared sequences? By sharing a sequencing with other rollups, a L2 or a rollup gives up its control over sequencing its L2 to attain interoperability. So now we can't run a centralized sequencer for better performance. Though, so the use of centralized sequencer was, in fact, first of all, to provide better UX for the consumer. But it can also be provided from a decentralized sense. But now since uh, even with the if I even if I have a decentralized sequencer, by sharing the sequencing rights, I'm not sure if my my rollup or my L2's transaction will be prioritized. And like even if I am a L2 and I want to like uh, be sequencing in a shared way, I want to provide my customers or the people on my chain with like better user experience. And with this way of using the central like a shared sequencer, it has now less performance than a siloed sequencer, and that is a big problem in itself. And the L2s now can't collect MEV, which they could collect before. So MEV only goes to the single sequencer that has now for now the rights, and it has given up control of censorship resistance. Uh, Also, because there is a chance that the sequencer that got the transaction got the sequencing rights can be a sort of malicious. So it can be like malicious in a way like it is not like letting uh letting any transaction from chain B go through. So and only from chain A it is like accepting transactions. So it will not be slashed on chain B, chain A, and but chain B can't do anything about it. So that is a problem or an issue. And now we can't modify or upgrade the operator that we have. So also that is an issue. So but so now Polygon came up with an idea of this aggregated layer. So what aggregated layer does is solve this problem, keeping in mind this problem of control sequencing. Polygon aggregation layer gives the benefit of atomic transaction. So atomic transactions is when in a shared sequencing scenario, what happens is if I am executing transactions on two chains, like if I am executing a swap transaction from chain L2 A to L2 B, uh, there can be a scenario that the first transaction goes through and the second transaction doesn't. So either I am getting a free mint from a chain or I am losing all my assets on another chain. If both of these transactions either have to go through in a like in the same block or like want should not be accepted at all, but it should happen for both of them. So this is the atomic transaction scenario. Either both of them will be accepted or both of them will be rejected. And with interoperability without the rollup giving the control of the sequencer, so uh, interoperability is there, and the control of sequencer of how if even I want a decentralized or centralized sequencer, the control is now given to the chain in itself. So this is the design of how Polygon's aggregated layer works. So all the sequencers first like generate a batch, and then for these batches, they generate a ZK proof of the updated state of the L2s, and then they all give it on the Polygon's aggregated layer. And what now this Polygon's aggregated layer does is it generates a single aggregated proof of all the proofs that it got from the sequencers for all the rollups. And after generating a single aggregated proof, it then posts it on a Ethereum's L1 chain. And in this way, uh, all the rollups can have interoperability. The sequencers, they have the right of sequencers, what sequencers they want to run. So ideally, it would be like all of them would be running decentralized sequencers, but they don't have to run a shared sequencer now. And with this, now interoperability is achieved, and their uh, sequencers control. They don't have to now give the sequences control for their rollups. So this is very beneficial in its own way and a very like innovative solution for this. Yeah, and this is all about the lecture for today. These are the references that I used. You can go through them. Yeah, and this is all about it.